Welcome and a very good day. So today we are going to cover chapter 4.5 on recycle, 4.7F on product separation, bypass and purge. So how do we illustrate the recycle descriptions into a block diagram? We can draw it in three ways. Okay. The first one is by having the recycle stream coming out from a downstream unit and connecting it to the fresh feed. If you have a multiple unit system as what we have here, the recycle stream can also come from or splitted from the product stream that is after your second unit going into the intermediate stream between the units, or it can also be recycled from the last units that you have in your process stream and it going back to your fresh feed. So they are two of the units that are also important in recycle as well as in bypass. The first one are the mixing point or the mixing unit, and the second one is the splitting unit. In actual processes, these two units might not be physically present. Okay, they can come in the forms of T-junctions or valves that control the ratio of the splitting amount. So you might have a valve there or a T-junctions. So you can see that when we have more than one unit, there are at least three possible ways of drawing a recycle stream based on the process descriptions given and what kind of materials that you want to recover from the process. Okay, how do we form the boundary analysis if we have more than one unit and the system is also having a recycle stream? So using the concept of boundary analysis that you had covered in the previous sections, where you have to identify a change in terms of the characteristic of the stream as the point of interest, then based on this given system where you have unit 1 and unit 2, as well as the recycle stream here, then we can develop 1, 2, and 3 subsystems, and also one overall system, giving us with 4 boundaries. As we mentioned previously, that we are treating the meeting point here of where the recycle stream is meeting the feed stream. So we are putting this as one unit where we can say it is mixing point or a mixer. So that will be one unit that we have. A second boundary is the unit 1, a third boundary is a unit 2, and the fourth boundary is the overall. If the process read differently, where it says that the recycle stream is coming out from the product stream or splitted from the product stream, and it goes into the feed stream, then we have to redraw it according to the second diagram here. So what we have here now is that we have different boundary that we are going to draw, where we have 1, 2, 3, 4, and 5 subsystems that we are setting up. Okay, the first one is the mixing point where your recycle stream meet with the feed stream. The second is your unit 1. The third is unit 2. The fourth is your splitting point. And the fifth is the overall system. But we have to note that our stream of interest are the incoming. Okay, let's say we have for Unit 5, so our incoming and our exiting stream are our point of interest. Any stream within the boundary, for example, the recycle stream here, the intermediate stream there, and stream between the splitter and unit 2 are not in our interest if we are analyzing or setting up material balance equation for system number 5. Let us see if we have a system with multiple units with 3 compounds that flow in as raw material into our process. Okay, here we have ethanol, acetone, and methanol. There are 3 units which we put here as A, B, and C, and bear in mind that this is a system without a reaction. What we have is just a mere maybe separation or mixing. So there are 3 units which we had labeled A, B, and C, assuming that there is no reaction and the system is at steady state, right? The system is at steady state, so we are able to identify the subsystems as 3 individual systems, okay, based on units A, B, and C. And then we have one subsystem which is combining unit A, B, and another subsystem that combining AC and an overall system. So in total, we can set up 6 boundaries, calculate their degree of freedoms, rank the degree of freedom, and set up the material balance equations. So for each of these, at least 3 equations can be developed for each system. But you have to make sure that, and you have to double check that all the equations that you develop are the real independent equations, right? We will see how to check the real independent equations, okay, in our example. Let's say if our system is represented by this diagram, okay. So in this diagram here, what we have is that we have 3 units A, B, and C, and in C, there are no purging stream that's going out. So basically, stream number 4 and stream number 5 are the same because there are no change in properties of the stream. We assume that C here is continuous. There is no accumulation within the units. So when we want to do our material balance calculation, we can check what are the checkpoints for us to set up the equations. For a non-reactive system, this is very simple. You have one mixing point that connects stream number 1, stream 1A, and stream number 4. So we can create a boundary analysis around this point here, and we can have the mass balance equations that represented by the mass flow rate of the compound that are present in stream number 1, stream number 4, and stream number 1A. The boundary analysis around unit A, okay, will take into account changes between stream 1A and stream 2. Okay, and the analysis on unit B will take into account the changes between stream 2, stream 3, and stream 5. So we can develop a mass balance equations that represent the overall mass balance around unit B, the independent molecular species of that are present in stream number 2, stream number 3, and stream number 5. For the overall system, Okay, for the overall system here, what we have to take into account are only stream number 1 and stream number 3. So we can set up the mass balance equations that relate stream 1 and stream 3 for the system and for all the subsystems as well. For all subsystems and the overall system, please remember to do the overall mass balance. Okay, overall the mass balance, as well as the one that reflects the component or the compound or the molecular species that are present in the system.